Hi, it's Double O Pi, your undercover chemist here. In my last video, I taught you how to calculate equilibrium constants from concentrations. If you haven't already watched that video, be sure to do so first so you can learn about how to make an ice table. In this video, you're going to learn how to calculate equilibrium concentrations from initial concentrations and an equilibrium constant. This is a lot harder and will require you to dust off your algebra skills. Are you ready? Let's go! So once again, this is a multi-step process, and I'm going to walk you through the steps first, and then we're going to apply them to some problems, starting with a fairly easy problem and then working our way up to a rather complicated problem. The first step is to make an ice table, as I showed you in the last video, showing all reactants and products, and you're going to fill in the known concentrations just like we did before. Now, in these sorts of problems, we don't have any equilibrium concentrations given. And so we can't calculate concentration changes with a simple addition or subtraction. And so what we're going to do is we're going to use algebra, and we're going to use x to represent one of the concentration changes. And then we're going to solve for the other changes in concentrations in terms of x. First calculating the changes in concentrations, and then calculating the equilibrium concentrations in terms of x. We can then use our table to write the expression for the equilibrium constant in terms of x. We will reorganize that expression so it's in the form of a quadratic equation, ax squared plus bx plus c equals 0. And then we can use the solution to the quadratic equation to solve for x. Then finally, we're going to take that value of x, put it back in our ice table, and use that to get actual numbers for equilibrium concentrations. I realize that this process does not make a lot of sense just by looking at the steps. So let's actually apply it to a problem. So here's a problem in which nickel oxide is being treated with carbon monoxide gas, and that is going to form solid nickel and carbon dioxide. And we're given the equilibrium constant at 1500 K. The equilibrium constants do vary with temperature. So it's important that we know the equilibrium constant at the particular temperature which we're working at. Okay, so we're starting with a mixture of solid nickel oxide and 0.45 molar carbon monoxide, and we want to know what the equilibrium concentration of CO2 is. So let's start with our ice table showing all the reactants and the products. Now, before we do that, let's talk about the equilibrium constant for this reaction. So we always start out by putting our concentrations of our products in the numerator of the fraction. So here our products are solid nickel metal and carbon dioxide. But we do not include in our equilibrium constant reactions anything whose concentration does not change, and that includes all solids. So we're not going to include our concentration of nickel metal in our equilibrium constant. And if you look over at our reactants, we also have a solid in our reactants. So our equilibrium constant is actually just going to look like this. It's just going to be the concentration of CO2 divided by the concentration of carbon monoxide. So when we make our ice table, we're just going to look at those two. We don't really care about the other concentrations because they are constant. We're going to fill in the known concentrations now, okay? So according to our product, we are starting with 0.45 molar carbon monoxide. So there we go. And do we know the other initial concentration? Yes, we're starting with no carbon dioxide, and so that's going to be 0. So now we're moving on to step 2, where we use x to represent one concentration change. So we're going to pick one of these, and since it's the first one, I'm going to pick carbon monoxide. We're starting with 0.45 molar. We're not going to make more carbon monoxide because in order to do that, we'd need some carbon dioxide, and we don't have any carbon dioxide. So we're going to be losing carbon monoxide over the course of this experiment. So we're going to say our change is x, and since we're losing it, it's going to be minus x. Now we can then do some math and see that our final concentration will be 0.45 minus x. So we started with 0.45, we took away x molar, and now we have 0.45 minus x molar. Okay, so now we go into step 3. We're going to use stoichiometric ratios to solve for other concentrations in terms of x. Okay, let's look at our stoichiometric ratios. For every mole of carbon monoxide we consume, that we use up in this reaction, we make 1 mole of carbon dioxide. We're consuming x molar of carbon monoxide, therefore we must be making, producing, gaining x molar of CO2. And now, of course, we can use that to calculate the equilibrium concentration. We had 0, we added x, we therefore end up with x molar at equilibrium. Now, step 4 is to write the expression for our equilibrium constant in terms of K. So let's start by writing the expression for the equilibrium constant. We already did that earlier. Our equilibrium constant is the concentration of carbon dioxide divided by the concentration of carbon monoxide. And we can take the values from the table and plug them into that. We have x for carbon dioxide, we have 0.45 minus x for carbon monoxide, and we're going to set that equal to the equilibrium constant value that we had in our original problem, which was 4.0 times 10 to the third. So here is an algebraic expression, and we need to reorganize it so it's in the form ax squared plus bx plus c equals 0. So the first thing we're going to do is we're going to multiply both sides by 0.45 minus x, and that gives us the following. X equals 4.0 times 10 to the third times 0.45 minus x. So let's multiply that out. Okay, we're distributing the constant through the parentheses. So x equals 1.8 times 10 to the third minus 4.0 times 10 to the third x. Now, we need to get everything on one side of the equation so that it's equal to 0. And so we're going to add 4.0 times 10 to the third x to both sides and subtract 1.8 times 10 to the third from both sides. And we end up with 4001x minus 1.8 times 10 to the third equals 0. So in step 6, we're supposed to use the quadratic equation to solve for x, but we don't actually have a quadratic equation here. We only have an expression in terms of x and a constant. There's no x squared. So we can just go ahead and solve this for x. It's pretty easy, and when we do, we get x equals 0.45. Now we move on to step 7. We have our value of x equals 0.45, and we're going to use that to solve for equilibrium concentration. So here is our original ice table, and we're going to take this value of x, 0.45, and plug it in to the table. So let's look at carbon monoxide first. X is 0.45. Equilibrium is 0.45 minus 0.45. So then that obviously means 0. There will be none left at the end of the reaction. Now let's look at carbon dioxide. The change was plus x plus 0.45, and that carries through to equilibrium, and we get an equilibrium concentration of 0.45 molar. So that is a really easy example of how to work these problems. And I say it's really easy because we only had to do very simple algebra solving for x. So let's think about our answer and whether or not it makes sense. So our equilibrium constant for this chemical reaction was 4.0 times 10 to the third. That's a pretty large value. And when we see a large value for the equilibrium constant, we normally think of a reaction that favors products. So we should have more products than reactants at equilibrium. And in fact, when we look at our equilibrium concentrations, we see that there's considerably more products than reactants. So our answer does make sense. So here's a more difficult problem. As I said before, the last problem only required simple algebra to solve, and that's pretty unusual. So we need to look at a problem that requires a lot more difficult algebra. So here is a reaction in which we have carbon monoxide reacting with water. This is in the gaseous state, to give carbon dioxide and hydrogen gas. We have a reaction mixture of carbon monoxide and 0.2 molar water, and we want to know what the equilibrium concentration of all the reactants and products will be. So we're going to start out, we're going to make our ice table showing all the reactants and the products, and we're going to put in the known concentrations. So here are the reactants on the left, carbon monoxide and water. Here are the products on the right, carbon dioxide and hydrogen gas. And I've abbreviated the table, so now we're just down to ICE for initial, change, and equilibrium. And let's fill in our concentrations. So the reaction mixture initially contained 0.250 molar carbon monoxide and 0.200 molar water. Now, how about the initial concentrations of carbon dioxide and hydrogen? Well, we didn't add any of those, and so our initial concentrations are going to be 0. Now we're going to use X to represent one concentration change. We need to pick one of these to be represented by X for a concentration change, and let's just start with the first one. Carbon monoxide is going to change by X. We start out with a lot of carbon monoxide and pretty much no carbon dioxide to make carbon monoxide from. So this is going to be a case where we're only going to lose carbon monoxide. So it's going to be minus X. And that gives us an equilibrium expression of 0.250 minus X. That's our concentration. Now let's go on to step 3, where we use our stoichiometric ratios to solve for all the other concentrations. So let's start by looking at water. Every time we use up a mole of carbon monoxide, we also use up 1 mole of water. So we are using up X moles of carbon monoxide. We are also going to use up X moles of water. And so therefore our equilibrium concentration for water will be 0.2 minus X. Let's move on to our products. For every mole of carbon monoxide we consume, we produce 1 mole of carbon dioxide. Again, I'm getting these stoichiometric ratios directly from the balanced chemical equation. So we have used up X moles of carbon monoxide. Therefore, we are going to produce X moles of carbon dioxide. And so our equilibrium concentration is going to be 0, which is our initial concentration, plus X. So it's going to be X molar carbon dioxide at equilibrium. For hydrogen gas, that works pretty much the same. For every 1 mole of CO we consume, we produce 1 mole of hydrogen gas. We have consumed X moles of carbon monoxide. Therefore, we're going to produce X moles of hydrogen gas, and so we'll have X moles at equilibrium. So now we have our equilibrium concentrations in terms of X, and we're going to write the expression for K in terms of X. So our equilibrium constant expression is going to have our concentrations of the products on the top and our concentrations of the reactants on the bottom. You'll notice that all the coefficients are 1. They're all raised to the first power. Now let's take our equilibrium concentrations in terms of X and plug them into that expression. So this is what we get. Now, if you look back at the original problem, you see that our equilibrium constant for this reaction was equal to 102. So we're now going to set that expression in terms of x equal to 102. And we can move on to step 5 now, where we reorganize the expression so it's in the form ax squared plus bx plus c equals 0. So first we're going to multiply so we no longer have a fraction. And you can see we have x squared equals 102 times 0.200 minus x times 0.250 minus x. And we need to multiply those together. So you remember how that works. You multiply the first in each parentheses times the outer ones in the parentheses times plus the inner ones of the parentheses, and then the last multiplied together. We end up with 0.05 minus 0.200x minus 0.250x plus x squared, or you can simplify that and get that expression. So let's take that expression, let's plug it back into the yellow underlined area, and this is what we get. Okay, it's still not in the form ax squared plus bx plus c equals 0. So let's keep on working through this algebra. We're going to multiply what's in the parentheses by 102, and we get this expression. And now we're going to rearrange things by subtracting x squared from both sides, and what we get is 0 equals 5.1 minus 45.9x plus 101x squared. And I'm going to flip that around so it's in the form that we like. 101x squared minus 45.9x plus 5.1 equals 0. Here is our expression for x, our quadratic equation. We're now going to solve this for x, and in order to do that, what we're going to use is the quadratic equation, which you may or may not remember from algebra. So what the quadratic equation says is that if you have a quadratic equation with the form ax squared plus bx plus c equals 0, the solution, actually it's going to have two solutions, x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. So and you end up with two solutions because you have to do negative b plus the square root of b squared minus 4ac over 2a and negative b minus b squared minus 4ac over 2a. So we're going to take that and we're going to use that to solve for x. So at the top here we see the expression that we derived earlier. So here's 101x squared minus 45.9x plus 1.275 equals 0. And below that you see the quadratic equation. Okay, so let's look at what our this would work out to be. Okay, we have x equals 45.9. That's b, right? That's the coefficient for 45.9x. So actually that coefficient is minus 45.9. And we have negative b, so negative 45.9, which is positive 45.9, plus or minus the square root of b squared, so that's negative 45.9 squared, minus 4ac, so 4 times a, which is 101, times c, which is 5.1, and we're dividing that all by 2a, so 2 times 101. Okay, so there it is, and if you multiply that out, you see that we get 45.9 plus or minus the square root of 2106.8 minus 2060.4 divided by 2 times 101. You'll notice that I write out all the steps. That's because most of the time when people get these problems wrong, it's because they messed up on the math. And so it's really helpful to have all the steps written out so you can go back and check to see what you did wrong. So now we're going to combine what's under the square root symbol, and you can see that comes up to 45.9 plus or minus the square root of 46.4 divided by 202. And that's 45.9 once you take the square root of 46.4. 45.9 plus or minus 6.8 divided by 202. Now, at this point, it's just simple arithmetic, but you can see that we are going to get two solutions. We're going to get one solution that's 45.9 plus 6.8 divided by 202, and 45.9 minus 6.8 divided by 202. So the first one, if you do the math, you end up with 0.261. And if you do the math for the subtraction for the second one, it comes up to 0.193. So now we have two possible values of x. How do we know which one is correct? To do that, let's go back and look at our ICE table. And if we look at the ICE table, it will become obvious which one we want to use. So that's step 7. In step 7, we're supposed to use that value of x in the ICE table to solve for equilibrium concentrations. So what happens if you use x equals 0.261? Well, if you look at the concentration of carbon monoxide, it was supposed to be 0.250 minus x. And if you use the value of 0.261 there, you end up with an equilibrium concentration of negative 0.011. Well, we can't have negative concentrations. Likewise, you could put that in for water. 0.200 minus 0.261 will give you negative 0.061 for a concentration. Again, you can't have negative concentration. So obviously that value of x does not work. And this is the way it will be with all of your solutions. You will always have two possible solutions. One of them will give you a concentration that does not work. And so let's go ahead and use the other value of x, 0.193, and let's put that in. So for carbon monoxide, we had 0.250 minus x, 0.250 minus 0.193. And you can see that we get 0.057. So you can take all of these expressions of x and put in our value of x, and you can come up with the concentrations. Now again, does our answer make sense? We had an equilibrium constant of 102 at 500 K. And because it's a fairly large value of equilibrium constant, we will assume that there's going to be more products than reactants. And in fact, that is what we see. We see a lot more of CO2 and H2. We have both 0.193 there, and only 0.057, 0.007 for your equilibrium concentrations of the reactant. Okay, now we're going to work on an even harder problem. It doesn't look hard at first because the reaction looks pretty simple, but it can be a bit tricky. Okay, so here is our problem. Our chemical reaction is the decomposition of iodine bromide. So we have two molecules of iodine bromide in gaseous form going to iodine gas and bromine gas. And we have an equilibrium constant, and you'll notice this is Kp rather than Kc, so we're using pressures. We're using atmospheres instead of concentrations, molarity, but it still works the same way. Our Kp value is 8.5 times 10 to the minus third at 150 C. So we are going to start by putting 0.05 atmospheres of iodine bromide in a 2-liter container, and we want to find what the partial pressure is after equilibrium is reached. So let's start at the beginning. Step 1, we're going to make an ICE table. And you can see that we have one reactant. So we have a pressure for iodine bromide in atmospheres. We have a pressure for iodine gas in atmospheres. That's one of our products. And we have a pressure for bromine gas in atmospheres. That's the other product. According to our problem, we have 0.050 atmospheres of IBR. Now, it doesn't say anything about the pressure of the iodine gas or the bromine gas. That's because we didn't add any, so those are going to be 0. Now we go on to step 2. We're going to use X to represent one concentration change. I have chosen to use X to represent the change in iodine gas. And we'll talk a little more about why we did that. It doesn't really matter which you choose. I felt this would be a little easier from an algebraic standpoint. But you could pick IBR if you wanted. Okay, so if we have 0 at the beginning and we add X, then our equilibrium concentration of iodine will be X. Now we can move on to step 3. We're going to use our stoichiometric ratios to solve for other concentrations in terms of X. Let's look at the other product. For every mole of iodine we also make 1 mole of bromine. So we made X moles of iodine, we also therefore made X moles of bromine. And then our equilibrium concentration will also be X. Now we're going to do the change for iodine bromide. For every 1 mole of iodine that we make, we consume 2 moles of iodine bromide. So we are going to we're going to get fewer moles of iodine bromide, and if we make X moles of iodine, we would therefore lose 2 moles of iodine bromide in the process. And therefore our equilibrium concentration is going to be 0.05 minus 2X. Okay, so now we're going to write the expression for K in terms of X. And first we have to write the actual expression for K. So now we're going to write the expression for K in terms of X. And before we do that, we first have to write the expression for the equilibrium constant Kp. And so we do that just the way we did when we were writing the concentration-based equilibrium constant. Here we're using pressures instead of concentrations, so we have the pressure of I2 times the pressure of Br2 times the pressure of IBr squared, because it has a stoichiometric coefficient of 2. And then we'll take our equilibrium concentrations that we calculated in the ICE table and plug those in to our equilibrium constant expression. And we're going to set that to the value for Kp that we got from the problem, 8.5 times 10 to the minus third. Now let's do algebra and try and get this reorganized into the form ax squared plus bx plus c. And the first thing is to multiply through so that we no longer have a fraction. So we're going to have x squared equals 8.5 times 10 to the minus 3, 0.050 minus 2x quantity squared. And so let's square that out. So let's multiply that out, and we're going to multiply the first terms in the brackets, 0.05 times 0.05, times the outer in each bracket, 0.05 times minus 2x, times the inner, minus 2x times 0.05, and the last, minus 2x times minus 2x, and this is what we get. And we're going to combine terms, and this is the value of that expression in the brackets. Let's take that, and again, we still want to get it in the form ax squared plus bx plus c equals 0, so we're going to multiply through the expression in the brackets by 8.5 times 10 to the minus third. And so here's what we get, and of course we can simplify that. Here's the simplification. You can check by math with your calculator if you want. And now we're going to, again, try to consolidate this all on one side of the equation. So we're going to subtract 0.034x squared from both sides, add 1.7 times 10 to the minus 3x to both sides, and subtract 2.125 times 10 to the minus fifth from both sides. And this is what we get. So here is our expression in the form ax squared plus bx plus c equals 0. And we now have it in the form where we can use the quadratic equation to solve for x. So remember again that the quadratic equation in the form ax squared plus bx plus c equals 0 has the solution minus b plus or minus b square root of b squared minus 4ac over 2a. And we're going to take our numbers and we're going to plug them in there. Okay, so negative b, okay, our b is 1.7 times 10 to the minus third, so we have negative 1.7 times 10 to the minus third plus or minus b squared, 1.7 times 10 to the minus third squared, minus 4ac, so we have 4 times a, 0.966, times c, negative 2.125 times 10 to the minus fifth, divided by 2a, so 2 times 0.966. So we're going to take that, we're going to simplify it further. You can see that once again I am combining the terms and then doing the addition. So now you can see that we have minus 1.7 times 10 to the minus third plus or minus the square root of 8.5 times 10 to the minus fifth divided by 1.932. And if you take the square root of 8.5 times 10 to the minus fifth, what we get is negative 1.7 times 10 to the minus third plus or minus 9.2 times 10 to the minus third divided by 1.932. So there's our expression. And again, we're going to have two solutions, one where we add and one where we subtract. So you see that if we add, we're going to get 3.9 times 10 to the minus third. If you subtract, we get negative 5.6 times 10 to the minus third. You can see that even without looking at the ICE table, actually, we have a value for x, which is negative. So here are our values, and if you look at our equilibrium pressures for both iodine gas and bromine gas, if you use the value x equals minus 5.6 times 10 to the minus third, we're going to get negative pressures, and we cannot have negative pressure, so of course the x must be the positive value. So let's take that value and let's plug it into our table. Okay, and we're going to get our equilibrium concentrations for both iodine and bromine are going to be 3.9 times 10 to the minus third, so that's x. And our equilibrium concentration for iodine bromide is going to be 0.050 minus 2 times 3.9 times 10 to the minus third. That's 4.2 times 10 to the minus second. Okay, so let's look at our answer again to see if it makes sense. We have a K value of 8.5 times 10 to the minus third. That's a very small value, and we'd see small values for K when we have more reactants than products. Is that what we have here? Well, we have our reactant that has an equilibrium concentration that has 10 to the minus 2, and both of our products have concentrations on the order of 10 to the minus 3. So there's about 10 times more products than there are reactants, and so that actually makes a lot of sense. This concludes our equilibrium problem solving videos. We will have more videos coming out in the future, so please subscribe to be notified of future uploads. Thank you for watching.